Hello and welcome. We are going to be, well, right after I pick up this pen that I dropped, good job. We are going to be tackling this electrostatics problem. If you're following along at home, you can find it in the physics textbook, topic 15, page 522. It is going to be problem number 8. I'll read the actual text and then we'll get right into it. I keep dropping things. 4-point charges are at the corners of a square of side A, as shown in figure, well, there. Determine the magnitude and direction of the resultant electric force on Q, with Ke, Q, and A left in symbolic form. Ke is the electrostatic constant, so we are luckily not going to have to pull that out of the calculator. And so what we have here is 4-point charges that are being placed. And the first thing that we want to notice is that they are all positive, which means that every force is going to be repelling, not attracting. The problem asks us to find the net force on this little guy, who has a charge of Q. And we know that the net force is going to be the summation of all the forces that act upon it. And so first thing we want to ask is what kinds of forces are acting upon it. In these types of problems, we're going to ignore gravity because it's convenient to do so. And we're just going to be looking at the electrostatic forces that these charges exert on it. So this charge is going to exert a force on our target charge here, the charge we're trying to solve for, and that force is going to be repulsive. So yes, this charge down here, if we're looking at these two charges, they are going to go apart, but we're only looking at this charge. So we know right off the bat that we're going to have some force. This isn't necessarily the resultant net force, but we're going to have some force going positive in the vertical direction. From this charge here, the repelling force is going to go this way, so we know that we're also going to have some force going in that direction as well. Another thing to note is that the magnitude of our forces, let's give ourselves a magnitude here, the magnitude of our force is equal to an electric constant from Coulomb's law times the magnitude of the charges, not whether or not they're positive or negative, divided by the square of the distance between them. So we know that since these two repelling forces have the same distance between them, because it's a square, and that they have the same magnitude of charge, Q, 2Q, Q, and 2Q, that these magnitudes are going to be the same. So I'll give us a little tick mark, just so we remember that. We also have one more charge that's exerting a force. That's going to be this guy over here. They're going to be repelling in this direction, and if this were a better square, then it would be much easier to see that it is going to go perfectly in the diagonal. And we will even, it'll be useful to draw in the geometry and the angles of this, so we even know that because it's a square, that this diagonal is going to be 45 degrees. So it looks like we're going to have 3 vectors, and we're going to have to put on our vector hats to be able to add them together properly. So to do that, we are going to split it up into components. So we're going to have a net force in the y direction, summation of force in the y direction, and we're going to have a summation of force in the x direction. So this is our x direction here. We're going to call this direction positive on the x, and we have a y direction, that's our vertical direction, and we're going to say up is positive, as is the convention, and we'll keep that convention for the purposes of this problem. So we have to ask ourselves first what sort of forces are acting in the y direction. We have the force that this charge exerts, that's going straight up, and we also have a component of this diagonal charge. If I break up this component up here, which I'll do over here, we have a diagonal charge acting on our lovely 1Q. A diagonal force, excuse me, not a diagonal charge. Diagonal force that is at 45 degrees, because it has to lie along the same line as their distance, that's 45 degrees. But you can also split this up into an x and a y component. So this has a little y component and a little x component. And we will touch back onto that later, but we know that in order to split it up into those components, we need the magnitude of this vector here. So to get the magnitude of this main diagonal vector, we are going to use our Coulomb's law equations here. So the magnitude of that vector is going to be Coulomb's electric constant times the magnitude of our first charge, 3Q, times the magnitude of our second charge, that's another Q, q 3q all over a squared. That's going right there. And so to find it in the y direction, we can use some geometric properties. We can use right triangle rule. We can do sine of 45. Either way will get us to that the y direction is going to be equal to the magnitude of the entire vector times the square root of 2 over 2. So our y direction force is going to be of magnitude equal to the magnitude of the main vector. That's this thing that I am going to copy here, all over a squared, times the square root of 2 over 2, times the square root of 2 over 2. It's getting a little tight here, but that's okay. We also have, less complicated to calculate, is the force from these two charges, and it's going to go straight up, so we don't have to do any right triangle or vector shenanigans. So we'll just add that right onto it. That force is equal to, again, our electric constant times the magnitude of our first charge, doesn't matter which one is which, times the magnitude of our second charge, all over, once again, a squared, because a squared is the distance between them. One thing, actually, that I made a slight mistake on, the distance between these two is not a squared, is not a actually, because it is the diagonal of a right triangle. I apologize for this in advance. Using our right triangle properties, this distance is actually rad 2a. And so when we get the rad 2a and we square that, that's actually going to be a 2a squared all over a 2a squared. So now we have our proper forces in the y direction. Now to do the x direction, you could follow the exact same steps, but you'll notice that since this is a 45-degree angle, the x component from our diagonal charge is going to be the exact same as the y component of our diagonal charge. So this is the same. And since this, the interaction of these charges is 2q, q, that's the magnitude of our charges. We have the same electric constant because it's a constant, and we have the distance of a squared. The same thing is in the horizontal direction. 2q, q, and the distance here is a. And we're going to square that to also get an a squared. So we know that this magnitude is also the same. So this is going to tell us that the magnitude of our forces net in the x and y direction on our target charge is the exact same in both the x and the y direction. That alone should tell us that that the net force, the resultant component, is going to go along the same direction here. It's going to be even longer because vectors get bigger when you add them, and it's going to be 45 degrees. So if you wanted to give yourself little compass rose, if this is north, then this will be perfectly northeast direction, and that actually solves part of our problem to figure out the direction. So now, what I'm going to do is we can simplify this to make it look less gross. So I'm going to go ahead and do that. The force in the y direction is equal to, I'm going to factor out the KE's, the a squareds, the what will eventually become q squareds. So let's go ahead and do that here. We have a KE. In both, I'm going to be multiplying and getting out a q squared, so we can pull those out. And I'm going to be getting an a squared on the bottom. And then we'll multiply that by whatever we have left. We have a rad 2 over 2 times 3 divided by 2. Rad 2 over 2 times 3 divided by 2. And that's just what's left from what I factored out. Plus, and then whatever's left from here, which is just a 2. So, if I am to multiply and add those numbers together, let's go ahead and do that. Root 2 divided by 2 times 3 divided by 2 plus 2. And let's go to decimal land. That's going to be 3.06. And then we'll carry on our variables, KEQ squared over a squared. That is the magnitude of our force in the y direction, summation of force y. Since the magnitude of the force in the y direction and the x direction are the same as we determined earlier, we can use our Pythagoras on our 45-degree right triangle. We will square the quantity of our force in the y direction, add it to the square of the force in the x direction, and then take the square root of that entire thing. And that is going to get us a total force. Here's our wonderful solution here. A total force of 4.33 times Coulomb's electric constant, Q squared, all over A squared. That's what you get from Pythagoras. That is the magnitude of our net force, and remember that that does not give us the direction. We know earlier that the direction is going to be northeast or up and to the right at a 45-degree angle. So that's the solution to the problem, and pat yourself on the back if you got it.